The monotonicity test states that if we have a one-variable function where the domain is an interval and the function is differentiable, if the derivative is greater or equal to 0, then the function has to be increasing. And also other way around, so it's an if and only if statement. And of course we could also flip this around and say that if the derivative is smaller or equal to 0, in that case the function is going to be decreasing instead. But you only have to prove it in one way, because it's essentially the same thing, you just have to switch all the signs. So for the proof, we have to prove it in both directions. So first we have to show that if the derivative is greater or equal to 0, then the function is increasing. To do that, we're going to use Lagrange's theorem. So we start off saying that the derivative is already greater or equal to 0 on the interval AB. And if we have a function that's differentiable on an interval, we can apply Lagrange's theorem, which graphically says that if you have an interval and we draw a line between 2 points, that would be called the secant line. There's going to be at least one point in between the values that we're going to call x1 and x2, where there will be a point that has a tangent line parallel to the secant line. So probably somewhere over here. And if two lines are parallel, that means that they have the same slope. And for a tangent line, the slope is a derivative. Well, for a secant line, you would need to find the y values here, which would be fx1 and fx2. And then use the usual concept of slope, which is just rise over run. So change in y over change in x. So we're going to start off saying that we take 2 points x1 and x2. Which are in our interval, a to b. And we can say that since these points satisfy Lagrange's theorem, there's going to be at least one point, which is this one. We're going to call it x bar. And also one little thing is that we're assuming that x2 is greater than x1, so it's to the right. So then we can say that there exists a point that we call x bar in between x1 and x2. Where the tangent line, which is going to have a slope equal to the derivative, will have the same slope as the secant line, which as we said before is rise over run. So fx2 minus fx1, so change in y, over change in x. Now, since we know that x2 is greater than x1, that was our assumption over here, so that just means that x2 is to the right of x1, then if you take x2 minus x1, that's definitely going to be positive. So the denominator is positive. And since we said at the beginning also that the derivative is greater or equal to 0 on the interval, then this over here must be greater or equal to 0. And so if we isolate the only part that we don't know, which is the numerator of the fraction, we're going to first multiply by the denominator. The idea is that if this is positive, or non-negative technically, because it could also equal 0, and you multiply it by a positive number, it's going to stay greater or equal to 0, which means that what's left, which is f of x2 minus f of x1, that must be greater or equal to 0. And if you solve for f of x2, we get f of x2 is bigger or equal to f of x1, which essentially is saying that the second y value is bigger or equal to the first y value. And this is exactly the definition of an increasing function. So we can say that f is increasing. So really all we did was apply Lagrange's theorem. We said that the derivative is greater or equal to 0 from the hypothesis that's assumed at the beginning. And this part over here is just referring to the x values. We're just saying that x2 is more to the right than x1. And then we just solve for fx2 minus fx1 to prove that the function is increasing. Now for the other part of the proof, we have to do the opposite. We're going to say that we know the function is increasing, and we have to prove that the derivative is going to be greater or equal to 0. So to do that, we're going to be using the definition of derivative and also the definition of an increasing function. So as we just saw here, if a function is increasing, it means that the second y value is bigger or equal to the first y value. We could use the same notation x2 and x1, but since we want to then combine this with the definition of the derivative, which is the one with the limit as h goes to 0 of the difference quotient, we ideally want to use the same kind of notation that we use there. So instead of using x1 and x2, we're going to modify the definition slightly. And say that for every h that's greater than 0, so for every positive h, f of x plus h will be bigger or equal to f of x. So x is just your starting point, and x plus h is a little bit more to the right. So this is basically your x2, and this is your x1 here. It's just slightly different notation. And so if we rewrite this, so if we bring everything to the left, we're saying that f of x plus h minus f of x is bigger or equal to 0. So if we then apply the definition of the derivative, that one says that the derivative is equal to the limit of the difference quotient. So limit as h goes to 0 of f of x plus h minus f of x divided by h. So we know from the beginning that h is positive. That was the difference between the x's. So the denominator is greater than 0. The numerator, we said over here that it's bigger or equal to 0. So if we're dividing a number bigger or equal to 0 by a number that's bigger than 0, you're still going to get something that's bigger or equal to 0. So all of this, without the limit technically, is bigger or equal to 0. Now if we take the limit of something that's bigger or equal to 0, here we'd be applying the permanence of the sign theorem. This is going back to limits from second partial. And essentially the theorem says that the sign is permanent in a sense that if what you have here is non-negative, then also the limit will be non-negative. And so all of this is also going to be greater or equal to 0 even with the limit. And so this proves that the derivative is greater or equal to 0 on the interval a, which is what we wanted to prove. So the other thing they can do is ask you for the strict monotonicity test. So this I'll write on the side. So the strict monotonicity is actually a quicker version of the same thing. The main difference is that it's not an if and only if proof, because it just says that if the derivative is greater than 0, then the function is strictly increasing, but it doesn't work in both directions. A counterexample of this is the function x cubed. Because x cubed, it's actually bigger or equal to 0, because at one point it's equal to 0, but it's still strictly increasing. So the point is that it doesn't go both ways. So if the function is strictly increasing, it doesn't necessarily imply that it's bigger than 0, the derivative. It could also be equal to 0 at some points. So since it doesn't go in both ways, we only have to do the first part of the proof. So you're really going to do exactly the same thing you did before, except that you're going to change the sign slightly. So this here will become a bigger than sign instead of a bigger or equal to sign, which is also going to affect this, and this, and this. And so in the end, that one will become a strictly bigger than sign, which implies that the function is strictly increasing. And as I mentioned, since the theorem doesn't work in both directions, you don't have the second part at all. So it's just a shorter version of the same thing. So the main thing to keep in mind is just that you have to only prove the first part.